Alright, so now that you've collected the data, let's take a look at it in Excel and start preparing it for your lab report. So as you can see in this setup, I've got the data just kind of in here as a simple data set. We have our raw data. We don't want to do anything with that data, but I'm going to go ahead and create the second page, go back, and I'm going to capture all the data at one time and pop back into the screen, paste it in. And it's oftentimes a good idea to get a quick glance at your data before you begin manipulating. You did this already when you did your previous lab activity with falling data, and now we're going to do that again and get a good look at it. But I want to kind of give you a bit of a shortcut here. So what we'll do is I'm going to highlight the first two items, first two columns, go to the insert. Most of the stuff at this point I'm going to assume that you've done at least enough times that you have a reasonable familiarity, so I'm going to just kind of bop, hit the stuff and move on. So as we did previously, I just am going to create a graph that is position versus time. I'm going to manipulate it a little bit so that I can fill up the space here. You'll notice that it doesn't fill up the entire space. I'm not really sure why this presets are that way, but it is what it is. So first thing that we'll do is, you see how I stretch it out because I want to be able to see all three graphs just like you saw in your pre-lab activity and in the capstone setup. So I'm going to zoom in like so. I'm going to go over here to quick layout. Let's go ahead and throw just all the basics in here. We need the axis title. This one's going to be position in meters. Pop over here and we'll do time as usual. Most of your horizontal axes are going to be time, and if you tap on the horizontal axis you can right click to format axis, unless you, as you can see, already have the format panel open. So I'm a format axis. In this case I'll just tap it for you to see. Well, you can't see the pop-up menu on this screen recorder, which is another obstacle. But so we come over here and you see it goes all the way 8 seconds. Let's change that 8.0 to 7.0 tab, and now that fills up the space better. You might get rid of these major grid lines. I like to go in there and put a solid, a solid border around. Make sure that's a solid black. And one other thing that I'm going to do is I'm going to take these data points that are blue, I'm going to go ahead and just make them, go over to marker, we're going to change those and make the fill solid black and no border. We're going to shrink them down a little bit too, because these are the guidelines for the eye. This is just the data. So we click here, stretch this out. I'm just playing with the formatting right now, and we'll leave this here. Oops. We'll leave this here for now, but a legend in this one is probably going to be a little bit less informative than anything else. Okay, so this is the rough draft of the data, and what I meant by a quick version of this is you can go ahead and highlight your column A and C, column A and D, and it gets a little bit time consuming on that, a little time consuming. So one thing that you can do, you've already got this format, it's already ready to go, so let's copy and we're going to go right below it and we're going to paste, and we're going to paste a third time because we want a velocity versus time and acceleration versus time. So squeezing these all into the view panel here, and I'm going to leave this format panel open because it might come into use. But now this is going to be velocity versus time, so let's change it to to velocity in meters per second, and then when you go back into once you get out of the axis title, you can right click or go select data, and instead of this is not position data, so we're going to edit this position data. We're not no other tricks. We're just going to change that name, point it to velocity versus time, and then instead of column A, I'm just going to type right here, and you can't see it, but you should be familiar enough with how to do it by now. Be careful not to use errors, but change your B's with C's. And if you do that and then just click OK, you don't even have to go and scroll or anything like that. You saw it change And now this is your velocity versus time data that you saw in Capstone. And there's some stuff that's going on there, and we'll discuss what that is. I think you probably would have guessed by now what that might be. And then we'll just do the same thing for the acceleration versus time. Let's change that title, acceleration versus time, and that's in meters per second squared. Can we do that if we go up to home and we launch the font window? Yes, and we go to superscript, and then there it is, meter second squared, formatted nicely. Right click on your data or the chart space, edit again. We're going to point the first one to acceleration versus time, D1, and then this is going to be column D instead of B. So, and it doesn't even have to be capital, just use lowercase, it'll automatically fix. And you change it to D, boom, and now you have your 3 graphs. That was pretty quick. Hopefully it'll feel as quick for you. What's really going to slow us down on this is, let's see if we can really pin down the best information to get from that. So let's take a closer look at the data here and try and come up with a way, see if we can figure out what we're looking at here, because looking at the data, analyzing the data, being able to understand what we see is a very key part of doing physics and doing science in general. For example, for a layperson like myself, looking at the heart rhythm, there's a bunch of bumps and creases and things that are going on in there, and they have very specific shapes that they should look like, that expert doctors need to be able to look at and immediately be able to recognize if something is where it's supposed to be or not supposed to be. So here in physics, we're going to start with this simple motion that you should recognize from your own data set. A couple things that we look for when we're analyzing data is the following. One, we want to know, is it smooth? Is the data smooth? If it's smooth, the chances are it's supposed, unless special situation where it's not supposed to be smooth, if it's smooth, then chances are that represents some characteristic of the data that we expect it to be, that the instrument is out taking data in a cohesive fashion, things of that nature. Second thing that we look for, is it fairly constant? Is it fairly linear? Is it a constant same value, or is there any trends that are kind of linear? We try and stick around linear for most data that we're looking at, because that's usually the easiest data to analyze. Finally, we also look for anomalies. Data that's sticking suddenly out of the way from what you're expecting the data to do. You expect it to be going on a smooth line, suddenly it jumps up and jumps back down. And so that's noteworthy data in the case. Now, in the previous lab, you may recall that we had nice straight lines, and because the data was nice straight lines of data. Here, we have chaos. Let's look at these 3 graphs here and see if they fit any of these conditions that we want to look for. So, first, position versus time. Why position versus time? Because that's the actual location relative to the sensor that you have, plus also looking at these 3 graphs, this is the smoothest. Smoothest, simplest, least complicated graph. And the first question we ask is, okay, well, we got this big curve. Is that one type of motion? You may recall at the beginning of the lab manual, there's a demonstration of a bunch of graphs, which I'll show here. So let's put up here constant velocity, constant acceleration of position versus time. And you can see that constant velocity, the position versus time is a straight line, just like it is right in this region here and in this region here. But for constant acceleration, which means that the object is actually accelerating in a constant motion, or generally smooth acceleration, we see that we should have a curve that looks like a parabola. And do we see any of that here? Well, we see that kind of in this area here, and we see that kind of in this area here, and finally in this area here. So for position versus time, we see elements of the graphs that we expect to see in these very simple situations. But now the question becomes, where do we pick one and start the, so the question now becomes, where do we start the constant velocity and start the constant acceleration? Are they allowed to overlap? And the answer is actually yes, they can overlap. They can be regions, because we're trying to do a best fit of the data that we think we see there. Sometimes there's going to be reasons when you say, this is exactly when the data starts. And there are some times when you say, it looks like it's doing this. In practice, you walking is a constantly changing state of motion. So walking backwards and then going forward, well, during that backing up and moving forward, you start to slow down and speed back up in the opposite direction. We want to see that in this data. And you'll notice about halfway along our process, we see that we have a curvature, not linear, a curvature that reminds us of constant acceleration, and that it's fairly smooth. Is it perfectly smooth? Not necessarily. But then the question becomes, where do we start and where do we stop? And this is when we can start looking at the other graphs to help guide us. So first, let's mark where we think the constant velocity and constant acceleration are. For constant velocity, I'm going to indicate with this pink marker. And right here, for constant acceleration, I'm going to use this blue marker. You'll notice that these overlap, and the reason they overlap is because until we make some decisions here, this region appears to be both part of the constant acceleration or part of the constant velocity that you think is happening. And we also have transitions here and here and here again. So we're going to have to look at the other data and see if we can use that to clarify what we're looking at. So the next question, we're looking at velocity versus time. We say, okay, is it smooth? It looks fairly smooth. Even though it's a bit jagged, a little bit rocky, it's moving around, it's doing a bunch of stuff, it's fairly smooth. The data points are fairly close to each other between one data capture and the next. So that's an indication of smooth. If it's not smooth, it'll be big jumps that are suddenly out of sorts, looks kind of chaotic, kind of like when you dropped your phone for the first lab activity, acceleration due to G. If the big jumps when it landed, and that was the sudden acceleration and bouncing on the ground, we don't see that here. We see smooth transitions between data points. Next question is it constant? In other words, does it hold some rate of constancy? Number one, we want if it's a constant value horizontally. That's a constant velocity. If it changes in a smooth way, that's a constant acceleration because, so let's show the graphs for velocity versus time, boom. So for constant velocity, you see it's a horizontal straight line, just like right here. And for constant acceleration, we see that it's in this here it's indicated as an upward slope, but any change of velocity that's a straight line that's got a slope to it corresponds to an acceleration, constant acceleration. So let's look at this and see. Again, in this region, we've got something going on here that we'll look at that in a moment, but for the most part, between this region here and here, we can see that the data kind of lives around this one constant value. So let me extend that for you, which looks to be around 0.4 meters per second. And then we also see a similar period of time right down here for constant velocity. Again, the pink constant velocity, which I'll do. And you can see that lives about negative 0.6. And immediately we can take a look at that and come up with a thing. Okay, this person who did this is walking about 0.4 in one direction, 0.6 the other direction. And if you think about what the mechanics are, what's going on when someone's doing this, always take a look at your data and go back in your mind what actually was going on in the lab. How does this connect to that? How can we build our understanding? And one way to think about that is we were walking backwards, then we were walking forward. Which one's a more natural movement? We're going to walk forward more comfortably. So walking forward is going to probably, and not surprisingly, be a faster pace compared to that. And we see that borne out here. Average appears to be about 0.6 compared to 0.4 here. What about constant acceleration? Well, for constant acceleration, we see that we've got this region right here where it's changing. It's got a downward slope. So we'll go ahead and add our estimation of what's going on there. And you notice I'm going beyond the data. When you did your trend lines, the trend line assumes interpolation. It goes in between the outer sets of a set of data and fills in the gaps there. Extrapolation is going beyond that data. And right now I'm just estimating a straight line, extrapolating past the data, but staying a straight line, so that we can kind of see where transitions are happening and make some decisions from there. Are there any other straight lines, constant, fairly smooth, constant data trends in here? And the answer is yes, there is. Right here at the beginning and here towards the end. Not all the way to the end, but closer to it. And when we look at this, we now can compare what we sketched here to what we're seeing on first one. We see, oh, wait a second, we have constant acceleration action that we can identify here, and constant acceleration action we can identify here. Constant acceleration, same here in the velocity versus time. Position versus time, velocity versus time. And you'll notice the time frames are fairly overlapping. Finally, we look at acceleration versus time and see what's going on there. Now, the challenge is that acceleration versus time seems much noisier. And I don't want to give away the secret here, but there's a reason for that noise. I want you and your lab mates to discuss and see if you can come up with the answer. Sometimes it'll be obvious, sometimes it'll take a moment to work it out. But even though it's noisier, and you might find connecting these data points with a connecting straight line will help you see the general trend. So now we're looking at acceleration versus time. Acceleration versus time for constant velocity, constant acceleration, and let's take a look. For constant acceleration, we expect, or for motion, now this is where we kind of get sketchy because we got velocity versus time, acceleration versus time, and now we're looking at these and compare them under the conditions of constant velocity, constant acceleration. It gets to be a word jumble, but what's the question here? The question is, where do we see constant velocity motion taking place? Where do we see constant acceleration motion taking place? And now we've got a couple spots that we seem to have identified for each type of motion. What about this third guy here? Let's take a quick look. You see here we have constant acceleration. Constant acceleration on the plot that corresponds to acceleration being non-zero. That would be this guy. The acceleration is not zero, it's constant, it's going horizontally. Same right here, it's non-zero, it's constantly going horizontal. Let's go ahead and mark that with our blue marker. Constant acceleration, I'll extend it a little bit. If we look anywhere else, is there anywhere else that this is happening? Well, kind of right here, there's a bumpy. This is where it gets tricky because it's such a short period of time and there's other dynamics that are happening. This whole set of data going from here to here are all away from zero. They're not centered at zero. So let's kind of put a mark. I'm going to put a mark right here. And it's going to be a little wall-eyed, but this is just for now for this one. But you can see it also lines up with the other two. This one lines up with the other two. Over here, we can expect, there it is, third one lining up with the third ones on the others. Again, kind of going average. And you see the accelerations are a similar value, about 0.5. Here, this is a little bit different, but that's because we have more to talk about with that. Under constant velocity, before we were looking at constant velocity first, now we're going to look for constant velocity motion in the acceleration versus time graph. For the acceleration versus time for constant velocity, you see that the line goes along the zero, and it's just zero. It's acceleration because the velocity is constant. Do we see that here? Well, not at face value. No, there's not. Their data's flopping all over the place. It's going crazy. But again, we want to think about, is it smooth in this area? Yes, it's smooth. It's fairly smooth. Is it fairly constant? There's a constancy in this region right here. It's still zero. Not zero. It's still moving, but in short bursts, it cancels itself out over time. And so on average, this appears to be constant and right around zero. Same right here. You see in this region, it goes fairly constant. So this is one way to look at the data. You always want to take a moment, look at the data, and what that means is look for, is it smooth? Look for, is it constant in some way? Constant speed, constant velocity, constant change, let's say. Constant of the graph, horizontally constant, as a function of time or whatever, or constantly changing in a smooth diagonal way in some way, shape, or form, or even has a smooth curvature that we can fit. Now, I'll go back and sit down at the desk and we'll go over adding in the data subsets in this case. So the next question you might have is, okay, when I go to put these graphs together, here we'll do that in a moment, how do I choose which segments to use? And that is a little bit more subjective. You gotta look at the data to see where you think the most convincing evidence of the type of motion that you're looking for exists. So let's talk about constant velocity. Constant velocity, that's the motion where the motion is changing at position with respect to time. Constant speed, that's what we got here in pink. Which one of these three, in your judgment, is the most convincing area of constant velocity? This region is fine, but it's hampered by the fact that it's not clear where we're starting and stopping. Acceleration versus time also is fine, but there's about 4 to 6 data points here where we're not clear where we're doing a transition between one type of motion and another. But if we look right here on the velocity versus time, notice we're definitely going up, and then we're definitely going horizontal in some fashion. So we can choose a point as a starting point for this around 2 data points. One of those two choices is going to put us in a nice spot that we are definitely at a transition point. And you can choose one to be part of the acceleration, one to be for constant velocity, and that's subjective. But then when you look for that on your other ones, it should help clarify what's going on there. So let's see. 1, 2, 3, 4, 5, 6, 7. Ignore that first dot. 1, 2, 3, 4, 5, 6, 7. 7, we put it right here. So let's see if that makes sense. Let's put a straight edge against it and see if the constant velocity does look linear after this point. You be the judge. Is this an exact perfect point to do this? Not necessarily. You can make an argument for this one. You can make an argument for here. This data point, the 6th data point of the velocity versus time, because it is still relatively within the region of some of these lower values along the rest of the range. Make a best judgment. By choosing these and then comparing the slope of this, the constant value here, and the average in this value, you'll be able to use that to compare and say, okay, these are in agreement or not in agreement. Similarly, we want to find where it starts and stops over in this point between constant velocity, constant acceleration. And again, we are seeing, okay, which one is the best one? Again, we're hampered here. We can see we got some smooth areas. We can kind of lay some foundations. But looking at the velocity versus time gives us some nice insights. And we might even gain something from the constant acceleration. So here we see that these two intersect right here at this guy. Because whatever this shaking is being muted by the fact that we're already in some form of change in velocity, some acceleration in this region. And over here, we overstep or overshoots, and then it goes back into this, whatever this bump is going on, this wobble. So again, we have a choice to make. Where's the best choice? Again, does it ultimately matter? If I went on either side of these, I think you would lose some information if you went to this one, this close up. But taking that point right there, so if you see, that data point starts at 3 seconds on the dot, so this is the next one after 3 seconds. And if we're not sure, well, this goes 1, 2, and then drops over and becomes a different value, negative. And if you'll notice, 1, 2, 3, 1, 2, 3, this seems to be right there on the cusp of crossing into negative territory for the curve to go the opposite direction. That's one possibility. Let's look at it down here. There's 3. We'll take this data point here instead, actually. Sorry. 1, 2, 3. Now we're at this maximum point of negative acceleration. So this could be like we're clearly in acceleration. This will tell you what the constant velocity is. Do you have to use this as the same point for constant acceleration? No, you don't. You can go a little bit further because remember there may be some acceleration stuff that's here because it's wobble, 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 and then goes flat. That's a little suspicious, especially since it continues wobbling elsewhere. So maybe there's some curvature here that's being muffled by the wobbling that's happening in the data. So we'll take that for constant acceleration. So this will be your constant velocity endpoint for this subset. And this we'll say, let's go to say right before 3. This will be constant acceleration data begin. Does that make sense? Let's look at 3. Here we have, this one is still below 0. That's consistent. You see these are all kind of negative. It's kind of drifted downward into the negative, and that's consistent with this dragging down a little bit as well as it's heading into an acceleration state. This is where you start slowing down to start turning around to walk the other way. What about the other side? Good question. Here it goes all the way down here. Again, we could take one of these as that, but the more the merrier. But at the same time, we see that we start to turn. Well, what happens over here? At data point at 4 seconds, we're the last one that's still negative before we've crossed over into positive here in the acceleration versus time. So if we take that up here, there's your 4 seconds. You see that we're already at midpoint. That's clearly transitioning into the constant velocity range in this region. So we'll take 4 seconds here as our boundary for this one. Hopefully this is clarified a little bit for you, making some choices. There is some subjectivity. You may feel like I have to make the right choice here, and the answer is no, you don't. You can make a few different, you can try a few different things. You can narrow this range a little bit if you want to, but then I would say you start looking at some calculation issues for your averages and comparing this to this and confirming that this is a 0. For constant acceleration here in this region, the more data points you get in this range, you can get a better curvature and a better fit. You can compare those values with the slope here and the average in this region. So the more you have to find a balance between the most data you can get that you feel still statistically fits within your assessment of that region as being part of one or the other. And for transitioning situations, there's not necessarily a hard and fast rule about this is definitely one, this is definitely the other. Try a couple different values in that range, see what you feel like fits best. Now, we don't need to capture all that information. We just need to find one region of constant velocity for the 3 data sets that's shared, and then one region of constant acceleration for the data sets that are shared. Let's deal with constant velocity first. Constant velocity, we expect that the position is going to be a straight line area, so that's over here and over here, these two areas. So I'm going to look at this and come over here and I'll say, well, the average is kind of all somewhere between, let's say, about 0.6 or 0.7 seconds all the way out to about 3.2, 3.1. So I'm going to use the range just to kind of be a little bit conservative here. You can go a shorter range in here and just use intermediate spaces in there, but I'm going to go ahead and just kind of do the full range to demonstrate that the overlap of the data points can be instructive as well. So for the position versus time, so that's it was 0.7 seconds all the way to 3.1 seconds. So I'm going to highlight that on all 3 graphs. So if I right click on the position versus time, I'm going to select data. We've got the position versus time. Let's change that name. We're going to call that raw. I know that we called it something a few minutes ago, just use the pointers, but that was a quick thing. So I'm going to call this raw position. Well, I'm just going to call it raw data. Then we're going to add constant velocity. Nope. Yes, constant velocity. We want constant velocity as the label because that's a condition of motion that's happening here. And then we're going to just simply go and capture that data. In the x value, we say we're going to go from 0.7 to 3.1. Remember, in your data, it'll probably be different data points. So make sure that you don't just arbitrarily capture this. You want to capture what works based off of the data that you're looking at that you collected. Click on this, come down, capture the position versus time for the condition of constant velocities. We've got some velocities and positions and everything that's kind of flying about. So let's make sure that we're clear on that. And you see the dots are populated in place. I'm going to go ahead and click OK. Click OK. You will want to change this, and I'll change it for this one, but I won't spend the time on the other ones just for time purposes here. But you'll want to change the marker to a different shape or make it larger. In this case, I'm just going to make them larger. Boop, 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 boop. And now it stands out a little bit more. Probably we'll also go with a different shape for the acceleration, but or you can make them open. So in this case, we'll leave that as is. Now I'm going to go to the other 2 graphs and reproduce this also for the same range. We're going to edit this. Data is no longer, this is raw. And we're going to add constant velocity. And if it's consistent, it should look like a constant velocity range. All we're doing is highlighting them so that we can see where those ranges correspond to each other. So that's the x's. And That's the Y. Also 0.7 to 3.1. We're using the same data range in both. And click OK, and then we'll come down to acceleration and repeat the process. Raw, click OK, add, constant, and you might even try to just kind of copy and paste. Be careful not to use arrows. 0.7 to 3.1, and this is going to go from the time 0.7 to the time 3.1 seconds. Click OK. Uh-oh. I used the velocity instead of acceleration. Let's fix that. So now you see what it's done. And you might think, okay, well, there's a little bit of a tilt here, but remember that these outliers here will cancel out these outliers here, and they overall will expect, we're going to do a calculation to confirm that the acceleration is either 0 or very close to 0. But now you can see the data points illustrated here for constant velocity. Now we want to identify constant acceleration. And the trick here is that your acceleration ranges are largely very narrow compared to the constant velocity. So which one is going to give us the best information? I think that the best information is probably the middle one. But you can consider doing the start or the finishing accelerations. Use the best data that you have to get the best judgment and make your best judgment from there. So in this range, I see that this data point, 3.1 seconds, can be maybe a little bit in line with the data. Maybe it's it's more clearly going out. I'm going to include it here. I want you to use your best judgment. That's what science is making your best judgment and doing the best you can. This comes all the way out here to about 4.0 seconds. So we're going to do from 3.1 to 4.0 seconds for constant acceleration, because it's really hard to nail it down with the acceleration information. The velocity information really is kind of the best graph to use for really selecting your data ranges. So let's go back up here. What we say, 3.1 to 4. So I'm going to right click up here, select data. We've already done that. Let's add constant acceleration. And for the time, we're going to go from 3.1 to 4.0. And then same thing for the position, 3.1 to 4.0, enter, enter again. And in this case, like I said, I'm just going to do the marker right here, but I recommend that you do that separately. So I'm going to make this one solid, and you always just kind of want to think about, what does this look like when it's printed in black and white? In this case, I'm going to put no fill, and I'm just going to make it really large. And now you can distinguish the solid dots, the solid large dots, the solid, the open large circles. Those are both data that you are selecting to do analysis with, and the small dots just represent the raw data. And there you go. You've described it in your notes or in your lab report. So we'll go ahead and go to the other two and add it as such. And I'm going to skip this part for you guys. Constant.
A few moments later.
And voila, there we go. All three of the data that you are identifying as condition of constant velocity and condition of constant acceleration. You can use your own shapes choices. I just want to give you the sense of where to go with this. These three graphs are ready, almost ready for just pasting into your lab report. And 3, 2, 1, there you go. Now it has also trend lines in particular places. In this particular lab, you can do trend lines for all these and still kind of get where you're going. But it's a little bit more direct if you just, or a little bit less steps if you just get the trend lines for your position versus time. You have a linear trend line for the constant velocity in a parabolic or a quadratic order 2 lab. And let me just kind of click on that so you can see that here. That's polynomial order 2. I said quadratic, but it's the same thing. Polynomial order 2 for the position versus time only. And remember, it's because it looks like it's a graph, and when we change it from linear to polynomial, the R squared value increases significantly from 0.68 or something to a really good fit. So There you have it, and you'll notice that the one shared data point has both data points illustrated the way that I've done it. And now the next step is to extract the data as seen in your lab manual and compare that to the average of the values. And the way you type the average of those values, you just simply highlight the values you were interested in. Well, you type equals average, open parentheses, highlight the data set that you want, close the parentheses, hit enter, and there's your number. Then you can calculate your percent differences between the average and the slope from the preceding graph, if you will, and put that into a table and put that into your lab.